So basically, let me try to explain again by using the same sketch. So basically, I started from a catchment and I said, let's assume that we can identify the position of the isochrones. And what are the isochrones? Are lines such that the travel time of the drops to the closure is the same for all the points that are lying over the line. So if I displace this isochron here at the time, let's say delta t, it means that all the points that are included in the area between the line and the closure have a travel time that is lower than delta t. That's fine. So it means that if a drop falls here on the line, it takes 1 hour to get to the closure where I want to express the air flow. If a drop falls here, it takes less than 1 hour to get here. Okay? And keep in mind that we refer to discrete time. So basically, when you say Q1, is not the this is not the river flow that you observe after 1 hour at that time instant. Q1 is an average river flow over the first time step. Because I realize that you may get confused because you may say after 1 hour the drop that full here is already passed, so I shouldn't include it in my computation. But when you refer to discrete time, you are expressing the variables as averages over the time step. So when I say Q1, it's river flow after 1 hour, meaning is the average river flow after 1 hour. Okay, so this is the first thing that you should consider when you refer to discrete time. Now, let's say that basically if I want to compute the river flow after 1 hour, I have to take into account all the drops that fell in the first hour. And where? In the area between the closure and the first isochron. Only these drops contribute to the river flow. Okay, good. Then, let me write, because I deleted here, so let me do this. Because I want to keep the integral there, because I need to talk about it. So after 1 hour, Q1, what is Q1? Is given by delta A1 times I1. Again, this is not the river flow that you get exactly after 1 hour. It's an average in the first time step. Okay, so I got all the drops that fell into the first hour, multiplied times the area that contributes to the river flow in the first hour. This is clear? Yeah, please.
Sorry, is I 0?
Oh yeah, 0, sorry, because I started with I started from 0, sorry for that, okay? And you may say, why do you start from 0? It would be clearer if you started from 1. It's because when you write the summation, it becomes the summation less complicated if you start from 0. Otherwise, you have to put in the summation a -1, which is, it becomes more complicated. It's just a matter of notation, okay? So let's say that in measuring rainfall, we start from 0, okay? So basically, what does this mean? Again, I0 is the rainfall that fell into the first hour. And delta A1 is the area that contributed to the river flow in the first hour. So it's reasonable to compute the river flow as by multiplying delta A1 times I0. Because it's rainfall times area. And you may say, yes, but rainfall also fell over the remaining part of the catchment. True. But the remaining part of the catchment didn't have time to reach the closure after the first hour, so I'm not considering it, okay? Okay. But then, as time passes, the remaining part of the catchment gets to the closure, and then I have to consider it. So let me say, Q2, what is Q2? So what happens between 1 and 2? Because before I considered the average in the first hour, now I have to consider the average of what happened between hour 1 and 2. So what happened in this second hour? First, rainfall continued, okay, because we assume that the hyetograph is continuing, okay, that's fine. So what happens is that now I have two areas contributing, delta A1 and delta A2. They are both contributing after 2 hours, but not with the same rainfall. Because delta A2 is contributing, given that the drops that fell over this delta A2 took 2 hours to reach the closure. They are the drops that rained 2 hours ago. Okay, so let me say that Q2 is delta A2 I0. I0 takes 2 hours if it falls over delta A2 to reach the closure. So this is what I have to consider. But then I also got rain from hour 1 and hour 2. So this rain, I have to consider it, but only from the area delta A1. Because the rain I1 started just 1 hour ago, so only the rain that fell into the closest area had time to reach the closure. So let me see, let me write delta A1 I1. This is the moral of the story. Let me see if everything is correct. Yes. So 2 hours ago times the area that takes 2 hours to get to the closure. 1 hour ago times the area that takes 1 hour to get to the closure. This is what's going on. I'm not sure if I was clear. Okay, it's better. What I did basically is to pass from this representation, which you may continue, Q3, let me continue, delta A3 I0. I0 from A3 took 3 hours to get to the closure. Fine. I'm computing the river flow after 3 hours. Plus delta A2 I1 2I1, yeah, correct, plus delta A3 I delta A1 I3 I2. Indeed, the fact that I start from 0 complicates a bit. Let me see. This is 1. Yeah. 0, 1, 2, 3, 2, 1. Okay. And then I transformed it in a summation, and then from the summation I got here. Yeah. This is, okay, this is delta A1, delta A2, delta A3. This is what?
So, I mean, this is separate from the delta A1.
So, say again?
Delta A2 is separated from delta A1, yes?
Yes, yes, of course. This is the reason, no, this is the reason why we are using delta, meaning an increment, okay? This is important. It's an increment. And also here you see that I am using an increment over time of area. Now, if you look at the whole model, then you understand that you could create a graph representing the progress over time of AT. you could do that. Because once that you identify the isochrones, you could represent in a graph the progress again along time of the contributing area. And this is without data. Be careful, this is just the contributing area, so this is the total. So this graph starts from 0, from the origin, and then after a time that is equal to the time of concentration, it gets to a point where you get the whole area of the catchment, A. Let me indicate with A the whole area of the catchment. And then you have to start from here and get here. But you may follow different paths. Let me just try something like that. What is this? This is the area time curve of the catchment. This is area time curve. And this is a behavior of the catchment. This is a typical behavior of the catchment. And it depends on the catchment shape. And also depends on the velocity of the drops over the catchment. Now let me make a couple of examples. What is the shape that this curve can take? I give some examples. Let's assume for now that the velocity of the drops over the catchment is constant, just an assumption, and therefore the curve only depends on the shape of the catchment. Let's suppose that you have a catchment that is, this is the river flow and this is the closure. Let's suppose that the catchment is very large at the beginning and then gets very thin around the river. Now, what is the shape of the resulting curve? What is the shape? You see that for a small time you have a quick increase, and then the increase is less rapid. Because you see that for the last part of the catchment you don't have a significant increase in area. So it takes time to get from here to here. So it takes time, but the increase of area is not so relevant. So you see that the catchment shape is dictating the behavior of this area time curve, and also of course the velocity of the drops. Because you may say that here you can have a very high velocity of the drops. And so if the velocity is very high, then of course you get a shorter time to get from here to here, and therefore the shape is different. But if you assume that the velocity doesn't change much, then it's the shape of the catchment then that determines the progress of the curve. There are some catchments that may have instead like this shape. So in this case you have the opposite. So you have an area time curve that doesn't increase much at the beginning, and then suddenly increases. An interesting situation is given if the area time curve is linear. you may say, why it's interesting? Because it's very simple. I will show you. It's very simple because, you know, I am interested in this derivative. To apply the model, I need the value of this derivative. Derivative of the area time curve versus time. And if the area time curve is linear, then the derivative is constant over time and takes the value of the slope of this linear curve. So it's interesting because here this becomes a constant. The derivative of a tau over time becomes a constant. It's an interesting case, it's simple. And actually, for many catchments, it's an approximation that works fairly well. So it's, as I said, it's an interesting case. Okay, now you have a series of slides here which depict the shape of the resulting hydrograph. Keep in mind, as you already know, that this model describes the whole hydrograph, not only the peak flow. You get a description of the hydrograph here. And you have a series of slides that tell you how the hydrograph behaves depending on the shape of the catchment. I'm not much interested in these cases. You see here you have the first case, the catchment is rectangular. You see in the slide, in the upper right part, you have the shape of the catchment, which is rectangular, and then it is assumed that the rainfall is constant over time, not varying, to make things simpler. And then you get this hydrograph for different times of rainfall. You see, duration, this D is duration 1 hour if rainfall lasts for 1 hour only, and you have a rectangular catchment, which means that the time area curve is linear if you take constant velocity. And then with a rainfall of 1 hour, you have this hydrograph. And the rainfall of 2 hours, the second one, and if the rainfall starts 4 hours, it lasts 4 hours, and 4 hours is the time of concentration of the catchment. You see, the catchment has 4 isochrones, which means 3 hours, so 4 hours of time of concentration. So if you have a rainfall that has the same duration of the time of concentration, you get the triangular hydrograph. And this is one case. Instead, next slide, if you have a triangular shape of the catchment, the time of concentration is again 4 hours. You have this hydrograph for different durations. I'm not much interested in these cases because, you know, it's already difficult to understand how the model works, and I don't want to really spend time in understanding these particular cases, but the first one which I showed in the slide before, I will take some time to develop it on the blackboard. But these next cases, I'm not asking it at the exam, so I'm not asking them at the exam. And there is another slide, you see, with a very, I don't know how to say in English, with that shape, I would say rhomboidal in Italian, maybe it's rhomboidal in English, I'm not sure. But if you look at the shape in the upper part of the slide, upper right, you see a particular shape of the catchment, and you get this hydrograph here. And this is another complicated case. I don't want to spend time on this. But I put the slides because I think they are interesting. Let me go back to this. As I said, the next one are just for your information. And okay, now let me spend some time on this case. And this case refers to rectangular shape of the catchment, which means that the time area curve, if you assume that the velocity of the drops is constant over the catchment, the time area curve is linear. And this is particularly interesting case because the rectangular shape is something that, you know, actually in practice it's often a good approximation. And let me also suppose that the rainfall may have 4 different durations from 1 hour to 4 hours. It's not specified that they are hours, but let's assume for clarity that they are hours, okay? They could be also days, it doesn't change anything. But let's suppose that they are hours. And the rainfall may have 4 different durations, but rainfall is constant, which means that if you have a duration of 4 hours of rainfall, it's constant over the 4 hours. Because otherwise it becomes more complicated, the shape of the hydrograph. If we can assume in this integral here that rainfall is constant and the derivative is constant, it becomes very simple to express the river flow and getting that shape, and I want to better explain how you get it. Okay, so let me delete something. In order to get this shape of the hydrograph, I want to refer again to the discrete case, because it's easier to understand. Even if I could refer to the integral, it doesn't change much, but I want to refer to the discrete case, because it's easier to understand, and also because, you know, here you see that we are referring to discrete times, so it's better to refer to the discrete case. And also it's better for me, because it gives to me, I am redrawing this picture here, because this is not rectangular. It gives to me the opportunity to explain once again how the summation is computed. So to clarify, to better clarify things. Okay, so let's refer to the hydrograph, to the catchment shape. I'm just redepicting what is depicted up there. So this is the catchment. Of course you have your river here, doesn't matter, the shape of the river doesn't matter. What matters is the fact that this is delta A1, delta A2, delta A3, delta A4. DC equal 4. And if you want to write down the area time curve, let me indicate with the time of concentration is 4. A is the total area of the catchment. And here you have 0, and then 1, 2, and 3. Okay, after 1 hour, you get here a value of delta A1. This is after 1 hour. So you get here. So the curve goes from here to here. After 2 hours, you get an increment from delta A1 to the value, from the value of delta A1 to the value of delta A2. get an increment from these two values. After 2 hours, what is the contributing area? It's delta A1 plus delta A2. And the increment from delta A1 to delta A1 plus delta A2 is delta A2. And the increment is the same. In the first hour, you have an increment from 0 to delta A1. Now you have an increment from delta A1, which is the same. So the slope doesn't change. If these areas are the same values, you get always the same increment in the total contributing area. And then you get a linear area time curve. Why it's linear? Again, because the increments, delta A1, delta A2, delta A3, delta A4 are equal. Is it clear? Okay, you can see that this is a simple case. Okay, let's suppose that you get 1 hour rain and then stop. Okay, so let's suppose that D is equal to 1. 1 hour of rain and then stop. Okay, so what is Q1? So first case, 1 hour rain. This is ID, and this is T. You have just 1 hour, okay? This is the first case. What is Q1? Okay, Q1 is delta A1 times I0. That's it. So basically you get here good. What is Q2? It's delta A2 times I0. And look, delta A1, delta A2, they are same value because it's my assumption, plus delta A1, I1. But I1 is 0. So this term is 0. Why it's 0 I1? Because I have just 1 hour of rainfall. It's just I0. I1 is no more rainfall. And then here, given that I0 is the same, you have the same value of river flow. And in fact, you see that after 2 hours, you have this line, which is just moving horizontally. It doesn't change the river flow. Okay. You can write the same relationship for Q3, which is equal to delta A3 I0, the same value, and Q4, delta A4 I0, same value. And in fact, you see that for 4 hours you have the same flow. And then after 5 hours you have river flow is 0 because after 5 hours you had rain for 1 hour plus the concentration time of the catchment is 4 hours. After 5 hours you have and everything is passed. The effect of rainfall is passed, and therefore you get to 0. And you can understand this because if I wrote here Q5, Q5 would be delta A5 I0. And delta A5 is 0. Because the concentration time is 4 hours, and then you don't have any increment of contributing area of the catchment for progressing time. That's it. Q5 is 0. And so you got an explanation for this first hydrograph. Okay, good. Now let's suppose that rainfall goes for 2 hours. And let me rewrite this, okay? And then let me write it here. 2 hours rain. And the hydrograph is, is like this. You have 2 hours, 1 and 2, same intensity. As I said at the beginning, we assume that the intensity of rainfall doesn't change, okay, to make it simpler. Okay, so what is Q1? Q1 is delta A1 times I0. And in fact, you see that you have the same value of river flow for all the considered hydrograph after 1 hour. That's fine. We have only the stern, because only the area delta A1 could reach the closure. So the other areas didn't reach the closure. And then let me write Q2. Q2 is equal to delta A2I1 plus delta I0 plus delta A1 I1. And what is the value of this? I doesn't change, and the increment of the areas, we said that they are the same, and therefore this is just twice the first one. So I wrote here the equal sign, let me write here, times 2. And in fact, this is what you see here. For the second hydrograph at Q2, here you have a value that is twice the value of the previous line. Okay. Then Q3 is equal to delta A3I0 plus delta A2I1 plus delta A1I2. But I2 is 0, and then this term vanishes, is not there, and then I can put an equal sign here. And if I move forward, I complete the description, and I get the second hydrograph, this one. And what's the difference? The difference is that the peak flow is twice the previous one. Fine. And there is another difference, which is the base time of the hydrograph. The base time of the hydrograph is given by the total duration of the hydrograph. You see that the total duration of the hydrograph, the base time, is longer with respect to the previous case. Why that? Because the base time of the hydrograph is given by the time of concentration plus the rainfall time. Again, the base time of the hydrograph, according to this method, is given by the time of concentration plus the rainfall time. And given that we assume that rainfall is lasting 2 hours, in the previous case it was lasting 1 hour, we have to expect a base time of the hydrograph that is 1 hour longer. And this is exactly this case. You see, the second hydrograph lasts 6 hours. The first one was 5. What's the difference? 1 hour, which is given by 1 more hour of rainfall. Now, the third case is similar. You just have the peak flow that is 3 times that of the first case, and the base time that is now 7 hours. Good. Let me don't write on the blackboard this third case. It's very simple. If you extend the second case, you easily get the third one. The fourth case, which I remind you, it corresponds to a rainfall that has the same duration as the time of concentration of the catchment. So the fourth case, which is characterized by a rainfall that has the same duration as the time of concentration of the catchment, is similar. What's the difference? First, I can identify in the fourth case, the last one,